Have you ever wondered if the ground beneath your feet is truly as steady as it feels? Right now, our planet is spinning faster than it has in decades, so fast that it's quietly rewriting the rules for everything from your phone's GPS to the global internet. Most of us never notice, but these invisible shifts are rippling through the systems we rely on every day. What's really happening deep inside the Earth, and why does it matter for all of us? If you're fascinated by the hidden forces shaping our world and want to stay ahead of the curve as science uncovers more, make sure to hit that subscribe button and turn on notifications. Your curiosity helps this channel grow, and together, we'll keep exploring the mysteries beneath our feet. Imagine for a moment the ground beneath your feet. It feels solid, unmoving, and reliable. But right now, as you go about your day, something remarkable is happening deep below the surface. The Earth is spinning just a little bit faster than it used to. Not so much that you'd notice while brushing your teeth or making your morning coffee, but enough that the world's most precise scientific instruments are picking up the change, tracking it down to the tiniest fraction of a second. Our days are ever so slightly shorter than they were just a few years ago. This isn't just a quirky fact for trivia night. The devices we use to measure time, atomic clocks, which define the very length of a second, are starting to drift out of sync with the actual rotation of the planet. And the reasons for this shift go far deeper than the surface, past the crust, all the way down to a place no human has ever set foot, a vast, swirling sea of molten iron nearly 3,000 kilometers beneath us. By the time you finish reading this, you'll have a clearer picture of what's happening to our planet right now, why it matters for everything from your phone's GPS to the global internet, and what the ancient rocks and fossils tell us about where we might be headed. Let's rewind to a seemingly ordinary day, June 29, 2022. On that day, Earth completed a full rotation in less time than at any other point since scientists began measuring with atomic precision. The day was shorter by 159 milliseconds. That's a blink, a sliver of time so small it seems meaningless. But when a planet that's been spinning for over 4 billion years suddenly starts rotating faster than ever recorded, scientists take notice. And this wasn't a one-off event. The record for the shortest day was broken in 2020, then again in 2021, and shattered in 2022. Year after year, the planet has been logging some of the shortest days ever measured. The forces behind this reach from the surface all the way to the planet's core. To really understand what it means for Earth to spin faster, you need to know something most people never think about. A day isn't exactly 24 hours. It never has been. We define a day as the time between one noon and the next, the interval from when the sun is highest in the sky to when it reaches that point again. But that interval isn't fixed. It changes, not by amounts you'd notice in a single lifetime, but by tiny fractions of milliseconds that add up over years and centuries. For most of human history, these changes have moved in one direction. The planet has been slowing down. The moon's gravity tugs at our oceans, creating tides that act like a brake, gradually dragging on Earth's rotation. Ancient coral fossils reveal that hundreds of millions of years ago, a year had more than 400 days. The days were shorter because the planet spun faster. Over time, that spin slowed. This slow deceleration has been the norm for eons. But something changed around 2016. The trend reversed. Earth began to speed up, not in a way you'd feel, but in a way that's measurable and consistent. This is where things get strange. The forces that have always slowed the planet, like the moon's tidal pull, haven't gone away. They're still at work. But now, something else is pushing in the opposite direction. strong enough to overcome that ancient drag. What could be causing this? The candidates are many, and they reach from the surface all the way to the core. At the surface, melting ice is shifting mass around the globe, physically altering the planet's spin. In the atmosphere, changing pressure systems push against the crust. In the oceans, shifting currents add their own subtle drag and release. And deep underground, that churning ocean of liquid iron, more than 2,000 miles below your feet, moves in ways that directly affect the rotation of everything above it. Each of these forces is real and measurable. What scientists are still working out is how they interact, which one is dominant right now, and whether the acceleration is building towards something bigger, or about to reverse again. What's certain is this: the planet isn't behaving the way our models expected. The systems we use to track time, synchronize satellites, and coordinate global infrastructure were all designed for a slower Earth. Now, they're running behind. And the growing gap between atomic time and Earth time is forcing a decision that could have serious consequences for the internet and beyond. It might sound like a millisecond here or there, doesn't matter. You can't feel it. You can't see it. If someone took a millisecond from your day, you'd never notice. But Earth isn't a person. It's a system of systems, all synchronized by the rhythm of its rotation. When that rhythm changes, even by a fraction of a millisecond per day, the ripple moves through every layer of that system. Here's why this matters. Every GPS satellite orbiting Earth was designed with a core assumption that the planet rotates at a predictable rate, changing only slowly and gradually. The same assumption is built into every power grid, every financial trading system, every air traffic control network. They were all built for a planet that behaves within a certain range. When the planet steps outside that range, even by milliseconds, synchronization starts to slip. The longer the mismatch runs, the further everything drifts from the timing it was calibrated around. The systems most vulnerable to that drift are the ones that tie our entire digital infrastructure together. GPS satellites orbit at a specific altitude and broadcast signals timed to nanosecond precision. They're synchronized to atomic time, which is based on the behavior of cesium atoms, not the planet's spin. When Earth turns slightly faster, the surface moves ahead of where the satellites expect it to be. The position data shifts, not by miles, not even by feet, but by centimeters. But in aviation, navigation, surgical robotics, and autonomous vehicles, centimeters matter. Financial systems are another area where these tiny shifts in time can have outsized effects. Think about the world's stock exchanges. Places like New York, London, Tokyo, and Frankfurt. Every day, millions of trades are executed, each one stamped with a time accurate to the microsecond. These timestamps are synchronized to coordinated universal time, which itself is anchored to atomic clocks. If the planet's rotation and atomic time fall out of sync, even by a sliver of a second, it can create confusion in the order of trades. In high-frequency trading, where fortunes are made or lost in microseconds, even the smallest ambiguity can mean millions of dollars are at stake. Power grids are another example where timing is everything. The electricity that flows through our homes and cities alternates at a fixed frequency, either 50 or 60 cycles per second, depending on where you live. Grid operators synchronize their systems to universal time to balance the load across vast regions. If time drifts even a little, the delicate balance can be thrown off, and the risk of blackouts or equipment damage increases. But here's a layer most people never think about. All of this was already anticipated. Scientists have long known that Earth's rotation isn't perfectly steady. That's why, back in 1972, they introduced the leap second. The idea was simple. Every so often, when the gap between atomic time and Earth time grew too large, an extra second would be added to the official clock. Since then, 27 leap seconds have been added. Not once has a second been removed. That's because, until recently, the planet was always slowing down, so atomic clocks always ran ahead. The fix was always to add time. Now, though, the planet is speeding up. Atomic clocks are falling behind. For the first time, the conversation has shifted to the possibility of removing a second from the official clock, a so-called negative leap second. And the engineers who keep the internet running have described this as one of the most dangerous things that could happen to global digital systems. Why is that? Well, computers expect time to move forward, second by second, in a predictable sequence. If you suddenly take a second away, you create a gap, a moment that never happens. Every system expecting that second, every log file, every transaction, every scheduled process tied to that moment, encounters a hole in time. Engineers at Meta have warned that a negative leap second could have a devastating effect on software that relies on precise timers or schedulers. Their suggestion: don't apply a negative leap second at all. Instead, they propose smearing the correction over a longer period, spreading the adjustment out so it's less jarring. But even that creates inconsistencies, because different systems smear time in different ways. During the transition, two systems comparing timestamps might be operating in subtly different versions of time. In 2022, an international standards body decided to eliminate the leap second entirely by 2035. That means atomic time and Earth time will be allowed to drift apart, with the gap to be handled by some other mechanism in the future. It sounds like a clean solution, but it really just postpones the problem. The gap is still growing, and it's growing in a direction nobody planned for. The systems most at risk aren't old or outdated. They're the satellites guiding every plane, ship, and self-driving car on the planet. Let's pause and think about what a negative leap second would actually mean. Every computer system on Earth expects time to move forward, second by second. Operating systems count those seconds. Databases timestamp every transaction. Networks synchronize by comparing those seconds across thousands of servers. The entire architecture of our digital world assumes that if you're at second 59, the next moment will be second 60. Then the clock rolls to zero and starts a new minute. A negative leap second breaks that assumption. The clock jumps from second 58 directly to zero. Second 59 never happens. Every system expecting that second, every log file, every transaction, every scheduled process, encounters a gap, a hole in time where something should be, but isn't. The internet runs on a protocol called the Network Time Protocol, which constantly synchronizes clocks across billions of devices. It was designed to handle time moving forward, not backward. When a system's internal clock suddenly reads 1 second earlier than it did a moment ago, processes scheduled to run at a specific timestamp can trigger twice. Logs that record events in order can show new events as if they happened before old ones. Security certificates that verify identity using timestamp matching can fail. In financial markets, the risks are even clearer. High-frequency trading systems execute thousands of transactions per second. Order books match buyers to sellers based on the precise sequence of submitted orders. If one exchange's clock jumps backward while another's does not, the sequence of trades becomes ambiguous. Transactions that appeared settled can become disputed. Trades placed after the subtracted second might be logged as occurring before trades placed before it. Power grid operators face a different version of the same problem. Grid synchronization relies on timestamps to balance electricity loads between regions. A sudden discontinuity in time creates a window where the coordination signal breaks down. In most cases, backup systems compensate quickly. But the industry has a term for what happens in the gap, a synchronization event. Even brief synchronization events can be the precursor to cascading failures that bring down large sections of a grid. Aviation adds another layer. Air traffic control systems depend on synchronized timestamps to track aircraft positions and resolve conflicts between flight paths. When controllers at different facilities are working from clocks that disagree, even briefly, the margin built into separation standards gets consumed by the ambiguity. Meta's engineering team estimated the risk was significant enough to argue publicly against ever applying a negative leap second. Google, Amazon, and Microsoft have all developed their own time smearing approaches as a workaround. None of these companies came to the same solution, which means that in the event of a negative leap second, the largest technology organizations on Earth would be running slightly different versions of time simultaneously. The standards bodies chose to eliminate the leap second going forward rather than face this scenario. But the underlying problem, a planet rotating faster than the timekeeping infrastructure was designed for, doesn't disappear with a policy decision. It just keeps compounding. And the engineers who maintain these systems know something most people don't. The force driving that acceleration isn't coming from the surface. It's not the ice. It's not the atmosphere. The deepest signal in the data points somewhere far more difficult to observe. Somewhere no human has ever been and no instrument has ever survived reaching. Every time you use your phone's navigation, there's a silent negotiation happening between your device and a network of satellites orbiting thousands of miles above the Earth. These satellites have one main job: they broadcast a timestamp. Your phone listens to signals from at least 4 of them, compares the tiny differences in arrival times, and uses those differences to pinpoint your location on the planet. The entire system depends on a single assumption: that the satellites know exactly where Earth is, not just roughly, but down to the centimeter. Each GPS satellite carries several atomic clocks and follows a carefully calculated path. Ground stations track these orbits constantly, sending updates to keep the satellites' position models accurate. The satellites, in turn, know where the surface of Earth should be at any given microsecond, based on the planet's expected rotation rate. But when Earth spins faster than expected, the surface moves ahead of the prediction. The error is small, maybe just a few centimeters or meters, but in some situations, that's the difference between a safe landing and a dangerous mistake. For a family finding a restaurant, it's trivial. For a cargo ship navigating a narrow channel at night, it could mean the difference between a smooth passage and running aground. For precision, guided aircraft or construction projects that require tunnels to meet perfectly from both ends, even a small error is unacceptable. Ground control teams are constantly correcting for variations in Earth's rotation. This isn't a new problem, and the systems have built-in margins. But corrections are applied in updates, not continuously. Between updates, the system operates on its last known model of Earth's behavior. When the planet accelerates in an unexpected way, those updates lag behind reality. There's another layer to this that doesn't get much attention in consumer tech news. GPS isn't the only global navigation system. Russia has GLONASS, the European Union runs Galileo, and China operates Beidou. Each system uses its own atomic clocks and ground correction stations. They're all coordinated to the same underlying time standard. But they don't update at the same moment, and their correction models don't always agree. When Earth behaves as expected, the differences are negligible. But when the planet's rotation changes in ways that push against the correction models, the disagreements widen. Devices that blend signals from multiple constellations to improve accuracy can start receiving contradictory position data. Aviation relies on this blended positioning more than almost any other industry. Modern instrument approaches at airports use satellite positioning to guide aircraft to within feet of a runway, even in zero visibility. The tolerances are tight, and the safety margins are real, but not unlimited. That's why agencies responsible for satellite navigation issue notices to air missions whenever unusual behavior is detected in timing systems. These aren't rare. Several have been issued in recent years specifically related to timing anomalies. The point isn't that the sky is falling. The systems are robust, and the engineers maintaining them are highly skilled. The point is that those engineers are working harder than ever to keep a planet-scale timing mismatch from creeping into systems that people's lives depend on. And the deeper question is why the planet started spinning faster in the first place. The atmosphere plays a role. The oceans play a role. The melting ice sheets play a role. But beneath all of that, there's a force so deep and so strange that understanding it requires imagining something almost impossible: an ocean of liquid iron, nearly 3,000 kilometers below your feet, moving in total darkness. If you could somehow drill straight down through the crust, through miles of rock, through the upper and lower mantle, and keep going past the point where the pressure is so intense that atoms themselves are forced into unfamiliar arrangements, you'd eventually reach the outer core. This layer begins about 1,800 miles down and extends another 1,400 miles further in. It's mostly iron and nickel, hotter than the surface of the sun, and entirely liquid, not like water, but like metal so compressed and energized that it flows in massive currents. These currents are driven by the temperature difference between the relatively cooler mantle above and the blazing heat of the solid inner core below. These flows aren't slow, at least not by geological standards. They move at tens of miles per year and carry electrical charge. Flowing liquid iron generates a magnetic field through a process called the geodynamo. The moving currents create electrical currents, which in turn create magnetism. That magnetism extends outward from the core, through the mantle and crust, and out into space, forming a protective bubble that shields us from charged particles streaming from the sun. Without it, the solar wind would strip away our atmosphere and make life on the surface impossible. But the liquid outer core does more than generate the magnetic field. It physically interacts with the rotation of everything above it. Here's where it connects to the speed anomaly. The outer core doesn't rotate at exactly the same rate as the mantle and crust above it. There's a coupling between them, transmitted through pressure and electromagnetic forces, but the core has some rotational independence. When the currents inside it shift, when massive columns of rising and sinking iron change their flow patterns, they exert torque on the layer above them. That torque is measurable in the rotation data. Researchers studying the relationship between changes in Earth's magnetic field and changes in rotation rate have found a pattern. When the field fluctuates in certain ways, the rotation tends to change as well. The connection isn't perfectly understood, and the mechanisms are still being debated. But the correlation is strong enough that geophysicists now treat core dynamics as a primary driver of decade-scale rotation variations. The acceleration that began around 2016 coincides with changes in the outer core's circulation pattern, detected in satellite magnetic data. The timing isn't a coincidence, and here's what makes it even stranger: the outer core doesn't move in isolation. It wraps around something at the very center of the planet, something solid, with its own rotation rate, its own angular momentum, and its own relationship with the layers above and below. At the very center of Earth, about 200 miles beneath your feet, there's a sphere of solid iron roughly the size of the moon. It exists in a state that defies ordinary expectations. The pressure at that depth is more than 3 million times what you feel at the surface. The temperature is about 9,000 degrees Fahrenheit, similar to the outer layer of the sun. At that temperature, iron should be liquid, but it's solid, forced into a crystalline structure by the immense pressure. The inner core sits suspended in the liquid outer core, with no physical connection to anything above it. No rigid structure holds it in place. The only forces acting on it are gravity, pressure, and electromagnetic fields from the liquid iron surrounding it. This means the inner core can rotate at its own rate, independent of everything above. For decades, geophysicists suspected that the inner core wasn't just sitting still, but actually spinning at its own pace, sometimes faster, sometimes slower than the rest of the planet. The evidence for this came from a surprising source: earthquakes. When a major quake happens, it sends seismic waves rippling through the earth, including straight down through the core, and back up the other side. Seismograph stations scattered around the globe record these waves, and by comparing the travel times of similar earthquakes over many years, scientists notice something odd. The waves that passed through the inner core were arriving at slightly different times than they had in previous decades. The best explanation: the inner core was rotating a bit faster than the mantle and crust above it, slowly turning relative to the surface. This subtle difference changed the orientation of its crystal structure, which in turn affected how seismic waves traveled through it. For a long time, this over-rotation was accepted as the norm, confirmed by multiple research teams using different data and methods. But then, in 2023, a study published in the journal Nature Geoscience analyzed decades of earthquake data and found that the inner core's rotation had slowed down. Around 2009 or 2010, it appeared to match the rotation of the mantle above it. Then, in the years that followed, it seemed to slow even further, possibly even reversing direction relative to the surface. In other words, the solid iron heart of our planet might now be spinning ever so slightly in the opposite direction from the rest of the Earth. That's a mind-bending idea. The forces involved are enormous. The inner core's angular momentum isn't trivial. When its rotation changes, that energy doesn't just vanish. It gets transferred, first to the liquid outer core, then to the mantle, and finally to the crust. Each transfer is imperfect, introducing delays and torques that ripple upward through the layers. Some researchers believe that the inner core's reversal is directly linked to the recent acceleration of the surface. The mechanism is still being worked out, and the data is still being debated. But it's clear that something at the center of the planet changed its behavior, and the effects are still traveling upward. The discovery that Earth's inner core may have reversed its rotation is one of the most significant findings in deep Earth science in decades. But it's also one of the most hotly debated. Let's clarify what's agreed upon before diving into the controversy. Seismic data covering about 60 years shows a clear pattern. The inner core was rotating slightly faster than the mantle and crust through the late 20th century. This rotation was consistent with models of how the core should behave under the influence of electromagnetic forces from the outer core and gravitational tugs from the mantle. What happened next is where things get complicated. The over-rotation appears to have slowed, and by some measurements, it stopped entirely around 2009 or 2010. The big question now is whether the inner core is currently in a static phase, matching the rotation of the mantle above it, or whether it has continued to slow and is now rotating in the opposite direction relative to the surface. The evidence for reversal comes mainly from the 2023 study, which looked at repeating earthquake sequences recorded at the same stations over decades. Their analysis suggested that the seismic signature of the inner core had flipped in a way that matched reversed rotation. Not everyone is convinced. Critics point out that the inner core's surface isn't perfectly smooth. It has valleys and ridges of iron crystal that could scatter seismic waves differently over time, without requiring a change in rotation. Changes in the structure of the outer core above could also affect wave travel times. But both sides agree on one thing. Something changed inside the planet. The inner core's behavior in the 21st century is different from what it was in the 20th. When the core changes its rotational behavior, it doesn't happen quietly. The connection between core rotation and surface rotation is rooted in the conservation of angular momentum. When the inner core slows down, that angular momentum is transferred, first to the outer core, then to the mantle, and finally to the crust. This transfer isn't instantaneous, it takes years or even decades to fully propagate upward. The timeline fits. The inner core's apparent deceleration in the late 2000s and early 2010s lines up with the surface acceleration that became measurable around 2016. That lag is scientifically interesting, suggesting that information from the center of the planet takes time to reach the surface. This raises a big question: if the inner core's reversal is real and ongoing, what happens next? What does the surface look like after all that angular momentum has worked its way upward? The answer might be written in the ice. While the core drives changes from the inside, the surface of the planet is also being reshaped by something happening at the poles, something that's accelerating faster than most models predicted just a decade ago. The physics here is straightforward. Even if the implications are not. Angular momentum is conserved. That's not just a theory, it's a fundamental law of physics. If you have a spinning object, and you move mass closer to the center, it spins faster. Move mass away, and it slows down. The total angular momentum, the product of how fast something spins and how its mass is distributed, stays constant. Earth is a spinning object. Ice sheets near the poles are mass-positioned close to the rotation axis. For most of the last 20,000 years, massive ice sheets covered large parts of the planet, especially near the poles. When that ice melts and the water flows into the oceans, it redistributes away from the poles and spreads across lower latitudes, moving mass away from the rotation axis. Pulling mass away from the axis should slow the rotation, and for most of the Holocene, that slow post-glacial rebound effect has been doing exactly that. But something has changed in the rate. The Greenland and West Antarctic ice sheets are losing mass at rates that have sharply accelerated since the 1990s. Greenland alone is now losing roughly 280 billion metric tons of ice per year. Antarctica is losing about 150 billion metric tons annually. These numbers are so large they can be detected from space. The scale of ice loss from Greenland and Antarctica is so immense that satellites can actually measure the change in Earth's gravity as the mass shifts. The GIRE satellites, short for Gravity Recovery and Climate Experiment, fly in tandem, tracking the tiniest changes in distance between them as they orbit. When a large amount of ice melts and the water moves into the ocean, the gravitational pull in that region weakens, and the satellites drift ever so slightly apart. This data gives scientists a direct map of how mass is being redistributed across the planet. The picture that emerges is striking. The poles are losing mass, while the mid-latitude ocean basins are gaining it. This shift in mass distribution changes Earth's moment of inertia, the rotational equivalent of how weight is spread out. According to physics, this should slow the planet's spin over the long term. And, indeed, the slow rebound of land that was once compressed under ancient ice sheets continues to pull mass toward the poles, acting as a brake on rotation that will persist for thousands of years. But in the short term, things are more complicated. The redistribution of mass isn't uniform. Different parts of the ice sheets melt at different rates, and the oceans don't fill evenly. Some basins are deeper, some are shallower, and the water spreads in complex patterns. This means the effects on Earth's rotation aren't just a simple sum. They interact in ways that can amplify or dampen each other. One of the most fascinating consequences is that the planet's rotation axis is physically moving. Not the magnetic pole, but the actual spin axis, the imaginary line around which the planet rotates. Over the past 2 decades, this axis has shifted by measurable amounts, and the direction of that shift lines up with the pattern of ice loss, especially from Greenland. Satellite data confirms this isn't just a model, it's a real, observed change. The implications of a shifting rotation axis are far-reaching. It affects everything from sea level projections to the long-term behavior of the magnetic field. But there's another, subtler signal in the rotation data: a wobble that, for reasons still not fully understood, nearly vanished in the early 2000s. Earth doesn't spin perfectly steadily. It wobbles, tracing out small, complex loops over time. Scientists have tracked these wobbles with increasing precision since the late 1800s. The one most relevant here is called polar drift, the slow, irregular movement of the geographic North Pole across the Arctic. For most of the 20th century, the pole drifted slowly toward northern Canada, mainly due to the ongoing rebound of land after the last ice age. But around the year 2000, the direction of drift changed, turning eastward toward Greenland, and the rate increased dramatically, from a few centimeters per year to about 17 centimeters per year. When researchers dug into the cause, the answer was clear. The primary driver was ice loss from Greenland. As Greenland's ice sheet shrinks, it changes the distribution of mass on the planet, pulling the rotation axis in a new direction. Western Antarctica's ice loss also contributes, nudging the axis further east. The result is that the actual geographic pole, the point directly above Earth's rotation axis, is now in a different spot than it was just a few decades ago. This isn't a dramatic shift you'd notice in daily life. It won't change where you see the North Star from your backyard. But at the level of precision required for satellite navigation, geodetic surveys, and time transfer infrastructure, it matters. Every system that relies on the exact location of Earth's rotation axis has to be updated to account for the drift. The International Earth Rotation and Reference Systems Service regularly publishes updated parameters, and these feed directly into the correction models used by navigation systems worldwide. The updates are coming faster now, and the rate of ice loss is still accelerating. There's a second-order effect that's even harder to calculate. The redistribution of mass from melting ice doesn't just shift the axis, it changes how the planet responds to other forces. One of those responses is a slow, rhythmic rocking called the Chandler wobble. For over a century, this wobble has been one of the most reliable features of Earth's rotation. But in the early 2000s, it nearly stopped. The Chandler wobble is a small, cyclical motion of the rotation axis, tracing a circle about 30 feet across at the pole every 14 months. It's caused by the fact that Earth isn't a perfect sphere, it's slightly flattened at the poles and bulges at the equator. For a rigid object, this wobble would eventually die out due to friction. But Earth isn't rigid. The crust flexes, the mantle flows, and the oceans slosh, constantly re-exciting the wobble and keeping it going. Superimposed on the Chandler wobble is an annual wobble caused by seasonal shifts in atmospheric mass and ocean loading. Together, they create a slightly irregular ellipse that repeats every 6 years or so. For decades, this pattern was rock steady. Then, around 2000, the amplitude of the wobble began to decrease. By 2005 or 2006, it had dropped to about 1/5 of its usual size, almost vanishing. This caught scientists' attention. Papers were published, and the debate began. What could suppress such a fundamental feature of Earth's rotation? The leading theory pointed to changes in deep ocean currents, specifically where cold, dense water sinks to the ocean floor. Shifts in these currents, possibly linked to a prolonged La Nina cycle, seem to dampen the excitation that keeps the wobble going. Eventually, the Chandler wobble recovered. But the episode raised an uncomfortable question. If ocean changes can suppress the wobble, what else might they affect? If the redistribution of ice and changes in ocean circulation continue at their current pace, the combined effects on Earth's rotation could push the system outside any behavior seen in the modern record. At that point, the only guide would be the deep past, ancient rocks, corals, and sediments that record how Earth behaved the last time conditions were similar. But there's another layer to this story, one that's unfolding right now over South America and the South Atlantic Ocean. In this region, Earth's magnetic field has weakened by more than 20% compared to its typical strength, and the anomaly is growing. Earth's magnetic field isn't a uniform shell wrapping the planet in a neat, even layer. Instead, it's a dynamic, shifting force, shaped by the turbulent flow of molten iron in the outer core. Most of the time, the field's variations are minor, stronger in some places, weaker in others, but generally stable enough to protect us from the solar wind and cosmic rays. Yet, there's one region that stands out, the South Atlantic anomaly. This anomaly is a vast area stretching over the South Atlantic Ocean and much of South America, where the magnetic field is significantly weaker than the global average. In the heart of the anomaly, the field is about 40% weaker than it would be at similar latitudes elsewhere. That weakness has real consequences, especially for satellites and astronauts. Normally, Earth's magnetic field deflects charged particles from the Sun, shielding satellites in low Earth orbit. But over the South Atlantic anomaly, the field is so weak that more radiation penetrates, increasing the risk of electronic malfunctions. The International Space Station takes extra precautions when passing through this region. Astronauts are warned, and sensitive instruments are powered down or shielded. This isn't a new phenomenon. Scientists have been tracking the South Atlantic anomaly since the 1950s. What's new is that it's expanding and deepening. Recent data even suggests it's splitting into 2 separate weak spots. The cause of this anomaly is tied directly to what's happening deep below, in the outer core. Under the South Atlantic, there's a peculiar structure in the outer core called a low-velocity zone, where the flow of liquid iron is different from the surrounding material. Some researchers believe this zone is a patch of reversed magnetic polarity, where the local field points in the opposite direction from the global field. The interaction between this reversed patch and the overall field above it creates the surface weakness. This reversed patch isn't static. It's growing, and that connects back to the story of Earth's rotation. Changes in the flow patterns of the outer core affect the magnetic field. Changes in the magnetic field, in turn, alter the electromagnetic coupling between the core and the mantle. That coupling influences how angular momentum is transferred from the core to the surface. So, the South Atlantic anomaly isn't just a hazard for satellites, it's a visible symptom of deeper changes happening in the outer core, the same region linked to the recent acceleration in Earth's rotation. The last time Earth's magnetic field weakened significantly on a global scale, something dramatic followed, a full reversal of the field. North became south, and south became north. This has happened hundreds of times in Earth's history, though the timing is irregular. The last full reversal, known as the Brunhes-Matuyama reversal, occurred about 780,000 years ago. Statistically, we're overdue. But that doesn't mean a reversal is imminent. These events don't follow a strict schedule. The gap between reversals can range from tens of thousands to millions of years. What's important is that reversals are a normal part of Earth's behavior. Life has survived every one of them. But survived doesn't mean unaffected. During a reversal, the field doesn't flip overnight. The transition takes thousands of years, and during that time, the field weakens dramatically, sometimes to just 10–20% of its normal strength. With less protection, more radiation reaches the surface, which could increase cancer rates, damage satellites and power grids, and disrupt animal navigation systems that rely on magnetic cues. Even atmospheric chemistry could be affected by the increased particle flux. Here's where the story loops back to rotation. The geodynamo that generates the magnetic field is powered by the same convective flows in the outer core that interact with the planet's rotation. The field and the rotation aren't independent, they're coupled. When the outer core's flow patterns change in ways that weaken the field, those same changes alter the electromagnetic torque on the mantle above, which affects the rotation rate of the surface. Researchers studying paleomagnetic records, traces of ancient magnetic fields preserved in rocks and sediments, have found correlations between periods of field weakness and anomalies in climate and geology. The relationships aren't fully understood, but they're real enough to keep scientists watching closely. What's especially relevant now is that the current rate of weakening is faster than the global average during non-reversal periods. The South Atlantic anomaly is the most visible regional symptom, but globally, field intensity has dropped by about 9% since the early 1800s. That's a significant change in less than 2 centuries. Whether this represents the start of a reversal, a temporary fluctuation, or something else entirely isn't clear yet. What is clear is that the field is behaving differently today than it did 200 years ago, and the outer core driving it is behaving differently than it did just a few decades ago. Meanwhile, the surface is spinning faster than at any point in the last half-century. These are all real, measured changes. The question is how they connect, and what their combined trajectory looks like over the next century. To answer that, scientists turn to the past. The history of Earth's magnetic field is written in stone, literally. When lava cools and solidifies, tiny magnetic minerals inside align with the direction and strength of the field at that moment. Once locked in place, they preserve a record that can last for hundreds of millions of years. By studying these rocks, paleomagnetists have mapped the field's history in remarkable detail, going back billions of years. But magnetic records aren't the only clues. Layers in seafloor sediments and ancient coral skeletons also preserve information about Earth's rotation. Corals, for example, grow in daily and annual increments, much like tree rings. Corals from 400 million years ago show about 400 growth rings per year, meaning days were shorter and the planet spun faster. Tidal rhythmites, sediment layers deposited by tides, also record the number of days in a year, directly tied to rotation rate. The geological record shows that Earth's rotation has been slowing for hundreds of millions of years. But within that long-term trend, there are periods of fluctuation, times when the rate of slowing changed, or even reversed for a while. These variations are driven by the interplay of tidal braking, core dynamics, and mass redistribution. The rocks and sediments of Earth are like a library, holding stories of the planet's past in their layers and minerals. When scientists look at the alternating stripes of magnetic polarity on the ocean floor, bands of rock that formed as lava cooled at mid-ocean ridges, they see a barcode of Earth's magnetic history. Each stripe marks a period when the magnetic field pointed in one direction before flipping. The width of each band tells us how long the field stayed in that orientation. These records are so detailed that they even capture brief events called geomagnetic excursions, when the field weakened and started to shift, but then snapped back without fully reversing. One of the most famous of these, the Laschamp excursion, happened about 42,000 years ago. During that time, the field's strength dropped dramatically, and evidence from caves, ice cores, and tree rings suggests that cosmic ray levels spiked, possibly affecting climate and even the extinction of some large animals. But the magnetic field isn't the only thing recorded in ancient rocks. The rhythm of Earth's rotation is also preserved, sometimes in the most unexpected places. Thin layers in seafloor sediments, called tidal rhythmites, show patterns tied to the number of days in a year. Since a year's length is set by Earth's orbit around the Sun, more days per year means shorter days, proof that the planet spun faster in the distant past. Ancient corals, too, keep a record in their growth rings. Corals from hundreds of millions of years ago show that there were once over 400 days in a year, each day lasting just over 21 hours. What's striking is that while the overall trend has been for Earth's rotation to slow down, the record isn't a smooth, straight line. There are periods where the rate of slowing changed, and even times when the planet briefly sped up. These fluctuations are the result of a complex dance between tidal forces, the shifting of mass on the surface, and the mysterious movements deep within the core. The last time Earth's rotation sped up on a scale similar to what we're seeing now was likely at the end of the last ice age, about 15,000 to 20,000 years ago. As the massive ice sheets that covered much of the northern hemisphere melted, huge amounts of water poured into the oceans, redistributing the planet's mass. The crust, freed from the weight of the ice, began to rebound, a process that's still happening today. This shifting of mass changed Earth's moment of inertia, and, as a result, its rotation rate. The parallels to today are not exact, but they're instructive. We're not in a glacial retreat caused by changes in Earth's orbit, but in a period of rapid ice loss driven by a warming atmosphere. The timescale is faster, and the geography of ice loss is different, but the underlying physics is similar. Mass that was once concentrated at the poles is moving toward lower latitudes. The crust is adjusting, and the rotation is responding. The geological record of the last deglaciation shows that these mass redistribution events don't produce smooth, gradual changes in rotation. Instead, they happen in fits and starts, with irregular jumps as different ice sheets collapse, and as pulses of meltwater enter the oceans. There were times when sea level rose by meters within just a few centuries. One event, known as Meltwater Pulse 1A, raised global sea levels by about 14 to 18 meters in just a few hundred years. The redistribution of that much water left a detectable mark in models of Earth's rotation. There's another fascinating connection: volcanic activity. During periods of rapid deglaciation, volcanic eruptions tend to increase. The reason is pressure release. Ice sheets are heavy, and when they melt, the pressure on the crust drops. The mantle rock beneath, already close to melting due to geothermal heat, becomes more likely to melt and rise, fueling more eruptions. Iceland is a prime example. Studies show that volcanic activity there increased after the last ice age, with a lag of a few centuries as the crust adjusted. Today, scientists are watching for similar signs in Iceland, Greenland, and West Antarctica, where subtle changes in subsurface pressure and seismic activity hint at the early stages of a deglaciation-driven volcanic response. The big picture that emerges from the geological record isn't one of sudden catastrophe, but of interconnected changes that play out over centuries. Each shift in mass, each change in rotation, each pulse of volcanic activity adds to a cumulative transformation that takes generations to fully unfold. What worries researchers today isn't any single measurement, but the fact that so many systems are changing at once, and that their effects may stack up in ways we haven't seen before. There's also a possible link between changes in Earth's rotation and seismic activity. In 2017, a study published in Geophysical Research Letters found that periods when Earth's rotation slowed slightly were followed, about 5 years later, by an increase in major earthquakes, those with a magnitude of 7 or higher. The proposed mechanism is that when the planet's rotation slows, the equatorial bulge shrinks, causing the crust at lower latitudes to shift inward. This movement puts extra stress on tectonic plates, nudging faults that are already close to breaking. The same logic works in reverse. When rotation speeds up, the equatorial bulge grows, stretching the crust outward and potentially triggering different types of earthquakes. The study's authors noted that we had just exited a period of slowing and entered one of acceleration, suggesting that the mid-2020s could be a period to watch for increased seismic activity. However, earthquake prediction is notoriously difficult, and most seismologists are cautious about drawing strong conclusions from correlations alone. The mechanism is plausible but not yet proven. On the volcanic side, the connection is a bit clearer. Changes in rotation affect the behavior of fluids beneath the crust, not just in the outer core, but also in the upper mantle, where partially molten rock can move in response to shifts in rotational stress. Some studies have found a weak but detectable link between periods of rotation anomaly and increased volcanic activity, with a lag of years to decades. The key point is that the effects of today's acceleration may not be fully expressed yet. The lag between changes in the core, the redistribution of mass, and the response at the surface means that what we're seeing now could be just the beginning. The planet is under more simultaneous stress than at any time in the modern record, and the combined effects are less predictable than any single change on its own. There's another major player in this planetary drama that often goes unnoticed: the atmosphere. We tend to think of the air as light and insubstantial, but in reality, Earth's atmosphere is a massive, dynamic system weighing over 5 quadrillion tons. It's not just a passive blanket, it's a moving, shifting force that interacts directly with the planet's rotation. When the atmosphere moves, when winds shift, when pressure systems build and dissipate, it actually pushes against the solid Earth. This isn't just a theoretical idea. It's something scientists can measure. Meteorologists and geodesists have spent decades comparing data on atmospheric angular momentum with records of Earth's rotation. The match is remarkable. When the atmosphere gains angular momentum, usually through the strengthening of large-scale wind systems like the jet streams the solid Earth slows down slightly to compensate. When the atmosphere loses angular momentum, the planet speeds up. The total angular momentum of the system stays constant, just redistributed between air and ground. The most obvious signal in this exchange is seasonal. In the winter hemisphere, jet streams become stronger, carrying more angular momentum. As a result, the solid Earth rotates a bit slower in the northern winter than in the summer. The effect is tiny, about a millisecond variation over the year, but with atomic clocks, it's measurable. There are also non-seasonal components, and some of the most significant come from events like El Niño. During a strong El Niño, trade winds weaken across the tropical Pacific, and the atmosphere transfers angular momentum to the ocean. This, in turn, affects the solid Earth's rotation. The El Niño events of 1982, 83, 1997, 98 and 2015-16 each produced measurable anomalies in Earth's rotation. The 2015-16 El Niño, one of the strongest on record, coincides closely with the beginning of the surface acceleration trend that scientists have been tracking. While El Niño alone can't explain the entire acceleration, it may have contributed to the initial departure from the baseline, with core and ice dynamics then amplifying the effect. The atmosphere isn't just a passive participant in this story. It responds to changes in the ocean, to shifts in ice coverage, and even to variations in the magnetic field, which can influence ionospheric circulation. All these connections mean that as other systems change, the atmosphere changes too, and its effect on rotation changes with it. For example, the jet stream pattern has shifted over the past 2 decades, partly due to Arctic warming. The stratospheric polar vortex, when it weakens and spills cold air southward, redistributes atmospheric mass and creates a brief but measurable pulse in Earth's rotation. The atmosphere, in this sense, acts as an integrator, receiving signals from ice loss, ocean warming, and core-driven magnetic changes, and rebroadcasting them as mechanical forces on the crust below. Every year, the atmosphere changes its contribution to Earth's rotation, and right now, it's changing faster than at any point in the modern record. But even with all this, the atmosphere isn't the only fluid system with a braking function on the planet. The oceans are doing something too, something quieter, but just as consequential for the long-term picture. If you've ever dragged your hand through water while moving, you've felt the resistance. On a planetary scale, the oceans create friction and pressure at the ocean floor, interacting with the rotating solid Earth. This interaction acts as a brake, slowing the planet's spin. It's a small effect compared to the tidal friction from the moon, but it's real, measurable, and, crucially, changing. Scientists track the angular momentum of the oceans, just as they do for the atmosphere. When ocean currents strengthen, they carry more angular momentum, and the solid Earth slows down a bit. When currents weaken, the planet speeds up. The deep ocean circulation system, known as the Atlantic Meridional Overturning Circulation, is a key part of this. It carries warm surface water northward along the eastern coast of North America and toward Europe, then sinks as it cools and returns southward as a deep, cold current. Recent studies show that the AMOC has been weakening. Multiple lines of evidence, sediment records, satellite measurements, and direct current observations suggest that this circulation is now at its weakest point in at least 1,000 years. The rotational implications are complex. The circulation transports angular momentum through the ocean basins in a specific pattern, and when that pattern changes, so does the distribution of angular momentum. Some changes would speed up the surface, others would slow it down. The net effect depends on the details of how the circulation reorganizes. What's clearer is the thermodynamic side. Warmer ocean water is less dense, so as the oceans heat up, they expand, raising sea levels. This isn't just because of melting ice. Warmer water itself takes up more space. As the upper ocean warms and the deep ocean slowly follows, the vertical structure of the ocean changes. The boundary between warm surface water and cold deep water, called the thermocline, deepens. This changes where angular momentum resides within the ocean column, and how it couples to the planet's rotation. There's another pathway connecting warming oceans to rotation storms. Warmer ocean surfaces fuel more intense and frequent tropical storms. A major hurricane is a rotating system that contains significant angular momentum. The formation and decay of these storms redistribute angular momentum between the atmosphere and ocean, leaving a mark on the planet's rotation. An ocean that produces more intense storms more often is one that perturbs the rotation budget more frequently. The cumulative effect of all these ocean changes isn't yet the dominant driver of the surface acceleration, but it's real, measurable, and growing. Among researchers, there's a specific threshold, a tipping point in the mathematics of the rotation system. That would change the conversation entirely. Some scientists believe we're closer to that threshold than we might hope. Not everyone agrees on what the current acceleration means. Some experts see it as a temporary fluctuation, a phase in the natural cycles of Earth's rotation that will eventually reverse. Others argue that the current situation is structurally different, driven by one-way trends like accelerating ice loss and possible regime shifts in the core. The honest answer is that both sides have valid points, and the data isn't yet sufficient to resolve the debate. What's clear is that the range of possible futures is wider than it was a generation ago. The system is less predictable, not because our instruments are worse, but because the planet is behaving in ways we haven't seen before. This growing unpredictability has real-world consequences, especially for the infrastructure that quietly supports modern life. The systems that depend on Earth's rotation for calibration, like timekeeping networks, satellite navigation, and power grids, were all designed with the assumption that the planet would behave within a certain, well-understood range. If Earth's rotation moves outside that range, those safety margins shrink, and the engineers responsible for keeping everything running have to rethink their strategies. There's a technical number that pops up in the literature about Earth's rotation and timekeeping that most people have never heard of. 1 second. Not just any second, but the accumulated difference between atomic time and Earth time that would force a negative leap second, even after the decision to eliminate leap seconds takes effect in 2035. The international standards bodies decided that atomic time and Earth time could drift apart, but only up to a limit, 1 minute. If the gap ever grows that large, a new correction mechanism will be needed. At current rates, it would take about a century to reach that point, but if the acceleration continues or reverses sharply, the gap could grow much faster. This isn't just a theoretical concern. Infrastructure systems are built to last decades. Power grids, communication networks, and satellite constellations are designed with a lifespan of 20 to 30 years. The systems being installed today will still be operating in 2050. Engineers have to make assumptions about what the timekeeping environment will look like over that window. If the current acceleration continues for another decade and is then followed by a rapid slowdown, the gap between atomic and Earth time could grow faster than anyone planned for. Systems calibrated to a slow divergence rate would suddenly find themselves out of sync. There's also a physical tipping point in the Earth system itself. Scientists studying the interaction between ice loss, sea level rise, and coastal geology have identified certain scenarios where feedbacks become self-reinforcing. As ice sheets lose mass, the land beneath them rebounds upward. That rebound changes the slope of the ice sheet, affecting how meltwater drains. If enough ice is lost, the drainage pattern can reorganize in a way that accelerates further melting, independent of what triggered the initial loss. These are the kinds of tipping points that are hard to spot until you've already crossed them. The connection to rotation is that rapid meltwater pulses, large influxes of water into the ocean over decades, rather than centuries, produce abrupt signals in Earth's rotation. The correction infrastructure we have now wasn't designed for sudden, large changes. And there's another threshold in the core. Models of the outer core's behavior suggest that its flow patterns can shift between two stable states, much like a ball can rest in either of two valleys. The current flow pattern, which seems to be linked to the surface acceleration, may represent one such state. If the system flips to the other state, the surface effect could reverse quickly. A planet that's been speeding up could suddenly start slowing down, and the gap between atomic and Earth time could grow in the opposite direction. Whether we're close to any of these thresholds is still unknown. But the systems that would be affected are already showing signs of strain. The idea that Earth's rotation affects daily life might sound abstract, but it's more relevant than most people realize. Take aviation, for example. Every commercial aircraft today relies on a combination of satellite positioning, inertial reference systems, and radio navigation aids. All of these are synchronized to coordinated universal time. When a flight crosses continents, the navigation computers track position continuously against a model of Earth's orientation in space. Any inaccuracy in that model translates directly into position error. Modern aircraft use GPS-based approaches that allow them to land in near-zero visibility, with tolerances measured in meters. The systems that make this possible depend on Earth rotating predictably. Aviation authorities have already issued technical bulletins acknowledging that increasing anomalies in Earth's geomagnetic and rotational behavior require more frequent updates to navigation databases. The update cycle for aviation navigation data has traditionally been 28 days, but some categories of data are now being flagged for more frequent review. Power grids are another example. They operate on alternating current at a fixed frequency, 50 or 60 cycles per second, depending on the country. Grid operators use time synchronization to coordinate the phase of current across interconnected systems that span thousands of miles. When two sections of a grid run slightly out of phase, energy doesn't transfer efficiently. If the mismatch grows too large, automatic systems disconnect the sections to prevent damage. These protective systems are calibrated based on decades of experience under stable timekeeping conditions. Unusual timekeeping, even subtle, can produce phase behaviors that fall outside the calibration range. Grid operators in Europe and North America have both published technical analyses showing that while current systems can handle today's level of anomaly, they'd need recalibration if the anomaly grows. Hospitals are perhaps the least obvious but most critical example. Modern hospitals are filled with time-sensitive systems. Medication dispensing logs every dose with a timestamp. Operating room equipment, especially anesthesia and patient monitoring, records data against synchronized clocks that form the legal medical record. Radiological equipment, like linear accelerators for cancer treatment, uses precise timing to coordinate with patient breathing. A 1-second discontinuity in the timekeeping system doesn't just create a data glitch. It can trigger safety alerts or even automatic shutdowns until the issue is resolved. Many hospitals have implemented mitigations since the leap-second crash of 2012, but mitigation isn't elimination. The deeper issue is that these systems are being maintained by teams who now spend more resources managing what was supposed to be a stable environment. The broader picture is that most engineering teams don't see the full scope of what's happening. When you lay all these signals on top of each other, the pattern isn't random noise. What's different now isn't that one thing is changing, it's that everything is changing at once. When a single system is under pressure, scientists can model and predict it. But right now, Earth is experiencing multiple, simultaneous changes across systems that usually move independently. And these systems are connected through feedback loops that amplify the changes in ways our models weren't built to predict. What makes this moment in Earth's history so unusual isn't just the number of changes happening, but the way they're all linked together. The planet's rotation is speeding up in a way we haven't seen in the modern record. The inner core has shifted its rotational behavior, possibly even reversing direction. The outer core circulation pattern has changed, which is showing up both in the planet's spin and in the magnetic field. The magnetic field itself is weakening, especially over the South Atlantic, where the anomaly is growing and splitting. The ice sheets are melting faster than climate models predicted, sending huge amounts of water into the oceans and shifting the planet's mass. This redistribution is moving the rotation axis and altering Earth's moment of inertia. Meanwhile, the oceans are warming, expanding, and changing their circulation patterns. The atmosphere is responding to all of these changes, feeding its own angular momentum shifts back into the rotation. And beneath it all, the geological indicators, like seismic patterns and subtle pressure changes in regions losing ice, suggest that volcanic and tectonic responses are only beginning to ramp up. Each of these changes is being tracked by its own community of scientists, using specialized instruments and publishing in different journals. But when researchers try to look at all these signals together, a bigger picture emerges. These aren't isolated events. They're coupled. The weakening magnetic field is a symptom of changes in the outer core, which also affect rotation. Ice loss changes both the rotation and the ocean circulation, which in turn influences the magnetic field's behavior. Atmospheric shifts affect rotation and also change where precipitation falls, which feeds back into ice accumulation and loss. These aren't just poetic connections, they're physical, measurable links. The result is a system that's moving in several directions at once, with each change amplifying the others. Scientists have a term for this: non-stationarity. It sounds technical, but it means something simple and a little unsettling. The rules that governed Earth's behavior for the last 10,000 years are shifting. The averages are moving, the range of variation is widening, and the patterns that held steady long enough for civilization to develop are no longer as reliable as they once were. The historical record, which we've depended on to predict what comes next, is becoming less useful because the planet is entering conditions it hasn't experienced in thousands of years. This isn't a reason to panic. Science has always adapted to changing systems. Monitoring networks are expanding, and models are being updated to account for new data. The scientific community is aware of what's happening and is working hard to understand it. But it does mean we need to be honest about how much we don't know and how wide the range of possible outcomes has become. The last time Earth experienced this many simultaneous changes, the evidence was left in the rocks and sediments that scientists study today. That ancient record shows that the scale of possible change is greater than most public discussions acknowledge. And there's one kind of visualization that's become increasingly common in research institutions over the past few years. A timeline that overlays all these independent data sets: core rotation, outer core angular momentum, surface rotation, ice mass loss, magnetic field strength, sea ice extent, and ocean circulation, against a common baseline. When you look at these time series together, a pattern jumps out. Each system shows a major departure from its historical baseline in roughly the same decade, centered around 2010 to 2020. Core rotation data shows a clear shift starting around 2009 or 2010. Outer core angular momentum estimates, derived from changes in the magnetic field, show a concurrent shift. Surface rotation data reveals the acceleration emerging from background noise around 2016, with the most extreme values in 2020 through 2022. Greenland's ice mass loss rate shows a step change increase beginning around 2012. The South Atlantic anomaly's minimum field intensity has been declining steadily, with a sharper drop in the mid-2010s. Arctic sea ice extent, a proxy for atmospheric circulation changes, shows its steepest multi-year decline starting around 2012. The Atlantic meridional overturning circulation, tracked through ocean heat transport and direct measurements, shows accelerating weakening in the mid-2010s. These data sets are measured independently by different instruments and different scientific communities. Yet they all show their biggest departures from the norm within the same 10-year window. The odds that this is a coincidence are very low. What it suggests is that these systems share a common driver. Something changed in the coupled Earth system during that decade, and the effects rippled across multiple layers at once. When Earth's geophysical systems enter a phase of simultaneous departure, the geological record shows that they tend to stay in that state for decades or even centuries before settling into a new equilibrium. And the new equilibrium is never exactly the same as the old one. That's the most important lesson from the past. After a period of upheaval, the planet doesn't return to business as usual. It finds a new normal. But it's important to remember that the planet isn't broken. It's not dying. Life has survived far more extreme transitions than this one, across hundreds of millions of years. What's different now is that human civilization was built during an unusually stable period, one of the calmest stretches in Earth's recent history. Our cities, infrastructure, and global systems were designed for a planet that didn't change much from year to year or even century to century. Now, those assumptions are being tested. The question that scientists are working hardest to answer isn't whether these changes are happening. They are. It's not even whether they're connected. They appear to be. The real question is how fast the transition will proceed, and whether the feedbacks will stabilize at a new equilibrium within the next few decades or keep accelerating. The difference between those two scenarios is enormous. If the system stabilizes soon, the engineering challenges are big but manageable. If the feedbacks keep amplifying, the window for adaptation narrows, and the risks to our infrastructure and way of life grow. The pace of change is what keeps scientists up at night. If the Earth's systems settle into a new balance within a generation, we'll have time to adapt. Our institutions, from power grid operators to aviation authorities, can recalibrate, update protocols, and build in new safety margins. The corrections will be significant, but they'll be within reach. But if the feedback loops between the core, the oceans, the atmosphere, and the ice sheets keep amplifying each other, the rate of change could outstrip our ability to keep up. In that scenario, the systems with the least redundancy, the ones already stretched thin, will be the first to show cracks. Their failures could cascade, putting pressure on other systems that were never designed to handle such stress. This is not just a theoretical concern. The more we learn about how tightly coupled Earth systems are, the more we realize that a change in one can drive changes in others. Improved monitoring and better models have revealed just how interconnected everything is. For example, a shift in the outer core's flow doesn't just affect the magnetic field. It also changes the torque on the mantle, which can alter the planet's rotation. That, in turn, affects the distribution of mass on the surface, which feeds back into the dynamics of the core. The atmosphere, too, is both a driver and a responder. Its changing winds and pressure systems can nudge the planet's spin, but they're also shaped by changes in ocean currents and ice cover. The planet you live on is not a static backdrop. It's a living, breathing system, constantly in motion, constantly adjusting. What's happening now isn't outside the range of what Earth is capable of, but it is outside the range of what Earth has done during the time humans have been here. The last 10,000 years, the period since the end of the last ice age, have been unusually calm by geological standards. That calm allowed agriculture, cities, and global trade to flourish. It allowed us to build infrastructure that assumes the ground beneath our feet won't shift too quickly, that the poles won't wander, that the days will stay roughly the same length. Now, every one of those assumptions is being tested, not in a sudden, catastrophic way, but in a steady, relentless direction. The planet is changing, and the systems we depend on are feeling the strain. The question is not whether we can adapt, but how quickly we can recognize the signals and respond. The honest answer from the scientific community is that uncertainty is growing, not shrinking. More data has revealed more change. Better models have shown us just how much a shift in one system can drive shifts in others. The planet is moving into a state that's less predictable, not because our tools are worse, but because the underlying conditions are further from anything we've seen in the modern record. This uncertainty has practical consequences. For example, the engineers designing the next generation of satellites, power grids, and navigation systems have to make decisions now about what the world will look like in 20 or 30 years. If the current trends continue, the corrections they build in today may not be enough. If the trends reverse, they may have overcompensated. Either way, the margin for error is shrinking. It's not just about technology. The way we manage resources, plan cities, and respond to disasters is all built on assumptions about how the planet behaves. If those assumptions are no longer valid, we need to rethink our strategies. That means investing in more flexible systems, building in more redundancy, and being ready to pivot as new data comes in. There's also a psychological dimension to this. For most of human history, the Earth has been a symbol of stability. The sun rises and sets, the seasons come and go, and the ground stays solid. When scientists say that even the length of the day is changing, it can feel unsettling. But it's important to remember that change is the planet's natural state. What's unusual is not that Earth is shifting, but that it was so stable for so long. The good news is that we have more tools than ever to monitor, understand, and respond to these changes. Global networks of satellites, seismic stations, and ocean buoys are feeding data into models that can track the planet's behavior in real time. International collaborations are sharing information and coordinating responses. The scientific community is more connected and more capable than at any point in history. But the challenge is keeping up with the pace of change. The systems we built for a stable planet are being pushed to their limits. The corrections that worked in the past may not be enough for the future. That means we need to stay alert, Keep investing in research and infrastructure, and be willing to adapt as new information comes in. At the end of the day, the story of Earth's accelerating rotation is a reminder that we are part of a living planet. Our technology, our cities, and our way of life are all built on a foundation that is constantly shifting. The more we understand about how the planet works, the better prepared we'll be to navigate whatever comes next. So, as you go about your day, remember that the ground beneath your feet is not as unchanging as it seems. The planet is spinning a little faster, the core is churning. The ice is melting, and the systems that keep our world running are working overtime to keep up. It's a story that's still being written, and we're all part of it. If you step back and look at the big picture, it's clear that we're living through a rare moment in Earth's history, a time when multiple planetary systems are shifting together, each amplifying the effects of the others. This isn't just a story about physics or geology, it's about how deeply our lives are intertwined with the rhythms of the planet itself. Consider how much of our modern world depends on the assumption that Earth's behavior is steady. Our cities are built at elevations that assume sea level won't change rapidly. Our satellite networks rely on the idea that the planet's rotation is predictable. Power grids, financial systems, and even hospital equipment are all synchronized to a clock that's supposed to tick smoothly, second after second. Navigation systems, from airplanes to delivery trucks, depend on the poles staying put and the surface moving at a known speed. But now, every one of those assumptions is being nudged by the planet's shifting behavior. Not in a way that causes instant chaos, but in a way that steadily increases the pressure on systems designed for a different world. The question facing scientists, engineers, and policymakers isn't whether these changes are real, they are. It's not even whether they're connected, the evidence suggests they are. The real question is how quickly the transition will unfold, and whether the feedbacks between systems will settle into a new balance, or keep accelerating. If the system finds a new equilibrium within a generation, the challenges are big but manageable. Engineers can recalibrate, infrastructure can be upgraded, and society can adapt. But if the feedbacks keep amplifying, the window for smooth adaptation narrows. The systems with the least redundancy, those already stretched thin, will be the first to feel the strain. Their failures could ripple outward, putting stress on other systems that were never designed to handle such rapid change. This is why the uncertainty matters so much. The more we learn, the more we realize how much we don't know. Improved monitoring has revealed more evidence of change, and better models have shown just how tightly coupled Earth's systems really are. A shift in one area can drive changes in another, sometimes in ways that are hard to predict. The planet is moving into a state that's less familiar, not because our tools are worse, but because the underlying conditions are further from anything we've seen in the modern era. For those responsible for planning the future, whether it's building new infrastructure, designing satellites, or managing resources, this uncertainty is a real challenge. Decisions made today will shape how well we can respond to whatever comes next. If the trends continue, the corrections we build in now may not be enough. If the trends reverse, we may have overcompensated. Either way, the margin for error is shrinking, and the need for flexibility is growing. It's not just a technical issue. The way we plan cities, manage water, and respond to disasters is all built on assumptions about how the planet behaves. If those assumptions are no longer valid, we need to rethink our strategies. That means investing in systems that can adapt, building in more redundancy, and being ready to pivot as new data comes in. There's also a human side to this story. For generations, the Earth has been a symbol of stability. The sun rises and sets, the seasons change, and the ground feels solid. When scientists say that even the length of the day is changing, it can feel unsettling. But it's important to remember that change is the planet's natural state. What's unusual is not that Earth is shifting, but that it was so stable for so long. The good news is that we have more tools than ever to monitor, understand, and respond to these changes. Global networks of satellites, seismic stations, and ocean buoys are feeding data into models that can track the planet's behavior in real time. International collaborations are sharing information and coordinating responses. The scientific community is more connected and more capable than at any point in history. But the challenge is keeping up with the pace of change. The systems we built for a stable planet are being pushed to their limits. The corrections that worked in the past may not be enough for the future. That means we need to stay alert, keep investing in research and infrastructure, and be willing to adapt as new information comes in. At the end of the day, the story of Earth's accelerating rotation is a reminder that we are part of a living planet. Our technology, our cities, and our way of life are all built on a foundation that is constantly shifting. The more we understand about how the planet works, the better prepared we'll be to navigate whatever comes next. So, as you go about your day, remember that the ground beneath your feet is not as unchanging as it seems. The planet is spinning a little faster, the core is churning. The ice is melting, and the systems that keep our world running are working overtime to keep up. It's a story that's still being written, and we're all part of it. The next chapter will depend on how quickly we can recognize the signals, how well we can adapt, and how much we're willing to invest in understanding the world beneath our feet. The planet has been through far stranger things than this, and life has always found a way to adapt. The challenge for us is to do the same, not just as individuals, but as a global community. If you've found this exploration meaningful, consider sharing it with others. The more people understand about the changes happening beneath our feet, the better prepared we'll all be for the future. And if you want to keep following this story as it unfolds, stay curious, stay informed, and keep asking questions. The Earth is always changing, and so are we. As we reach the end of this journey through the hidden changes happening beneath our feet, it's worth reflecting on just how extraordinary this moment is. The planet is not in crisis, but it is in transition, a transition that is subtle in some ways, dramatic in others, and deeply interconnected across systems we often take for granted. Every measurement discussed here, whether it's the shortening of the day, the shifting of the magnetic field, the melting of polar ice, or the changes in ocean and atmospheric circulation, has been confirmed by independent teams using the most advanced instruments humanity has ever built. These aren't just theories or computer models, they're real, physical signals, observed and tracked by scientists around the world. The Earth is spinning faster than it has in decades. The inner core's behavior has shifted. The outer core's flow is changing. The magnetic field is weakening, especially over the South Atlantic. The ice sheets are losing mass at rates that surprised even the most cautious climate models. The oceans are warming and circulating differently. The atmosphere is responding in ways that feed back into all the other systems, and the axis around which the planet spins has moved. All of these signals, when mapped together, point to a shared origin. A period in the last decade or so when something in the coupled Earth system changed, sending ripples through every layer from the core to the crust to the sky. The question that remains is not whether these changes are real, but what comes next. Human civilization, for all its technological prowess, was built during a rare window of geological calm. The last 10,000 years have been unusually stable by Earth's standards. The rotation varied only slightly, the magnetic field was relatively steady, the ice sheets retreated at a manageable pace, and sea levels rose gradually. In that stability, we built cities at the water's edge, created global networks that depend on precise timing, and developed systems that assume the planet's behavior will remain within a narrow band. Now, those assumptions are being tested, not by catastrophe, but by a steady, persistent shift in the background conditions. The infrastructure that supports our lives, navigation, power, finance, healthcare, transportation, was designed for a world that doesn't change much from year to year. But the world is changing, and the systems that keep it running are being asked to adapt faster than ever before. The scientific community is working urgently to understand how quickly these transitions will play out. If the feedbacks between systems stabilize soon, the challenges will be significant but manageable. Engineers and policymakers will have time to recalibrate, upgrade, and adapt. But if the feedbacks keep amplifying, the window for smooth adaptation narrows, and the risk of cascading failures grows. What's remarkable is that, despite all this, the planet is not in danger of breaking. Life has survived far more extreme transitions, mass extinctions, supervolcanoes, asteroid impacts, and magnetic reversals. The Earth is resilient, and so is life. The real challenge is for human systems, which have never had to operate across a geophysical transition of this scale and speed. So, what can we do? The answer is both simple and profound: stay curious, stay informed, and stay flexible. The more we invest in monitoring, research, and international cooperation, the better prepared we'll be to respond to whatever comes next. That means supporting science, building infrastructure that can adapt, and fostering a culture that values resilience over rigidity. It also means recognizing that uncertainty is not our enemy. It's a signal that we need to pay attention, to keep asking questions, and to be ready to change course as new information emerges. The planet is not a static backdrop for human activity. It's an active participant in our story. The more we understand about its rhythms and feedbacks, the better we can align our systems with the realities of a living world. As you finish reading this, take a moment to appreciate the quiet marvel of standing on a planet that is always in motion, always evolving. The ground beneath your feet is part of a vast, interconnected system that stretches from the churning iron of the core to the swirling clouds above. The changes happening now are not a sign of doom, but a reminder of how dynamic and complex our home really is. If you found this exploration thought-provoking, consider sharing it with others. The more people understand the hidden forces shaping our world, the more resilient our societies can become. And if you want to keep following the story of Earth's changing rhythms, stay engaged with science, support curiosity, and remember that adaptation is one of humanity's greatest strengths. Sleep well tonight, knowing that you're standing on a planet that has weathered far stranger times than these, and that the systems watching over it, from satellites to seismic networks, are among the most sophisticated tools ever created. The story of Earth's rotation is still being written, and we are all part of its next chapter. Thank you for joining me on this journey. If you'd like to keep exploring the wonders and mysteries of our planet, consider staying connected, whether that means subscribing, sharing, or simply keeping your curiosity alive. The Earth is always changing, and so are we.